and we were discussing about like, these charges. Initially we considered that they are the static point charges and the influence of a few more static charges that are in the immediate vicinity of them. So this is what we discussed, and we saw that, essentially, ideally, initially, this is the Gauss's law. And then, then we went for like, the law associated with the first, it was Coulomb's law. Okay. Coulomb's law, then, it translated into Gauss's law when we considered the geometry. Correct. And then now we are considering them to move. Right. And when I'm considering them to move, I am considering a kind of a steady current here. This is important to note down that this is a steady current. I mean, that means, right now I'm not considering any fluctuation. So if I make an electrical arrangement, like I have a battery here, and then I'm making a steady current, I may just see that although this is electron, they should always repel each other. But, if I can just, reverse the flow direction, I may see that there is an attraction. And from where you get the first hint of the magnetic field. Okay, this is the first experimental proof that, you may have the magnetic field. So the hypothesis that has been put forward that if a charged particle is moving at a uniform velocity of v, okay, it generates a magnetic field B, and the force that is associated with that field is V cross B. And that force is called the Lorentz force that is originating from the magnetic field. So essentially, when you have an electric field, statical charges, and then the charges are moving, so you have a kind of total force that is coming out to be F equal to Q is the charge, into E plus V cross B. E is the electric field and B is the magnetic field. Okay. Now, one very interesting thing you will find out. So you know that work done is nothing but F is the vector dot dl. Okay, dl is the displacement. So force into displacement is your force into the dot product between force and displacement is your work done. Now force we know, magnetic field force we know Q into V cross B, and dl we know that V dt. If you multiply, now you see here V cross B means is a vector which is perpendicular to V. Perpendicular to V as well as perpendicular to B, right? So if you take a dot product with V, that will become, since it is perpendicular to V, the dot product will be 0, right? So although it appears that magnetic field do work, but net work done by a magnetic field is always 0. Magnetic forces do not work, right? So this is a basic elementary proof that the magnetic forces, they do not work. Now we had a lot of confusions related to the current. Okay. Now, first thing what you have to understand, what is a current? Current is, when the charges are flowing, okay, charges starts flowing, that is what we call the current, right? The current in a wire is a charge per unit time, right? But question is that whether this charge per unit time is a scalar, vector, or a tensor. Up to this point, we consider this to be a scalar quantity, which is lambda V. Lambda, you know that what is lambda? Lambda is your is the one that we have decided, that charge per unit length, right? But over a period of time, what you realize that current is nothing but a vector where this V is nothing but, this is not speed, but this is the velocity. So I is equal to lambda into V. How we really incorporate in the force equation this? So force is equal to V cross B. Now V cross B into dq, and this dq you know that you can write as lambda dl, sigma dA, and rho d tau. These are the three different ways you can write this dq. This is, charge per unit length into differential length, charge per unit area into differential area, charge per unit volume into differential volume. So this is the force in a volumetric situation. This is the force on a surface, and this is the force on a line, right? Now, when you do that, you see that this, if you multiply this lambda inside, so what happens? You get V into lambda, that is I cross B. Okay. Now that also you can write as I as a scalar, and then DL. DL means you take the length part, which is the direction part, into this DL cross B, right? Which becomes like, in case of area vector, it becomes K, and case of volume vector, it becomes J. So J is essentially what? J is the current per unit area perpendicular to the flow. So how do you define J? J is DI. This is the I vector. This is the current that is flowing through this particular geometry, and dA is the area perpendicular to that. So this is the flux associated with the charges that are flowing across this wire. So it is a typical wire-like situation. At the same time, J is, that this is nothing but rho into V, charge per unit volume into the velocity. This is by definition J equal to rho V, right? And in order to define the total current, what you need to do, you need to do a surface integral over the area. J dot dA, total I, integral I, this is becoming total I, and J dot dA across the surface integral. And if you take a divergence, you get a, if you use the Gauss divergence theorem, J dot dA becomes divergence of J d tau. Now, if you equate these two, equate this one to this one, you end up getting the continuity equation or the charge conservation equation for an electric field, where divergence of J is minus del rho by del T. So this is one very, very fundamental equation. This is called the continuity equation from the electric field. What is the idea? Idea is that Q into V is for a point charge. This is summation. This is for discrete electrostatics. So for a line, this is I into dl. For a surface, K into dA. And for a volume, this is J into d tau. So Q can be written as lambda dl, sigma dA, and rho d tau. Okay. So we have to remember this one fundamental equation where rho is the charge density and J is what? J is the current per unit area perpendicular to the flow. And J is a vector. J is a vector. Divergence of J is a scalar. Now, stationary charges, note down this particular point very carefully. Stationary charges leads to constant electric fields and electrostatics. Whereas steady currents, when the charge started flowing, steady means there is no time component. So what I'm doing, say here, there was a time component. So steady means del T will be 0. So divergence of J equal to 0 for a steady current. The magnetic field is constant, and that is what is called the magnetostatics. And we'll see later on, we'll go for the magnetodynamics as we progress, as we bring in these time-dependent quantities with the Faraday's experiments. Now, in that sort of situation, magnetic field of a steady line, so suppose you have a loop, and through that there is a current. So you can consider DI to be the vector. Okay. Now, if this Di to be the vector, and if R to be the reference point with respect to you are measuring this current, which is defined by the joining vector R, which is the position vector. So Biot-Savart law is defined as the magnetic field B is defined as mu by, mu is the magnetic field, permeability, magnetic permeability of the free space. So mu 0 by 4 pi into I cross R. I cross R. Okay, this R vector, this is the R point through which the position vector R is there. So I cross R divided by R square into dl. This is the equivalent of the Coulomb's law for the magnetic field. Okay, so this is for a line I cross R square dl, and for a volume this becomes mu0 by 4 pi j r by r square into d tau. So this is charge per unit volume. This is charge per unit length. This is called the Biot-Savart's law, in which mu0 is the magnetic permeability of the free space, which is 4 pi into 10 to the power 7 Newton by ampere square. And B is the magnetic field, which has a unit of Tesla or Gauss. There are two units. CGS is Gauss and NKS is Tesla. Now, look at the whole way the things are going on. So you take this, you know, cyclic integral of B dl, right? You just evaluate cyclic integral of B dl for us. There is a point mass and it is generating this magnetic field, right? Now, if you take cyclic integral of B dl, you replace Biot-Savart's law. This is a constant that comes out. So you have cyclic integral of dl. Dl is the length, which is nothing but 2 pi s. 2 pi s is the perimeter. So it comes out to be mu0 into I. That means, you know, if you now apply this Green's theorem where B dot dl is getting converted into what? Del cross B. You can write this, you know, you remember, you know, B dot dl can be written as what? B dot dl can be written as del cross B into dA. There was an identity, right? Now, when you convert to A in terms of A, then this becomes J. I becomes J dot dA into mu0. And then if you simplify these two, you get del cross B equal to mu0 J, which is the Ampere's law. So B from the Biot-Savart's law, if you just do a kind of cyclic integral over the field, magnetic field, you get the one of the fundamental laws of the Maxwell's equation, del cross B equal to mu0 into J, which is Ampere's law, which is applicable for only magnetostatics. You will find that there will be a correction coming, Maxwell's correction coming later on to modify this. So for simple things, you know, when the magnetic field, you know, when there is a steady current, this is appropriate, Ampere's law. But when there is a fluctuating current, you know, you will find that, like, you know, AC field, you will find it will be associated with another term, which will be coming from the electric field. Right? So del cross B is equal to mu0 J. And if you consider B to be this, and then if you take a divergence of that, right, del cross J equal to 0 by definition, and this is also equal to 0, you use a vector identity, you straight away get del dot B equal to 0. So these are the, so we had del dot E equal to rho by epsilon, del cross E equal to 0, del cross B equal to mu0 into J, and then del dot B equal to 0. Straight away, we have 4 equations. So electrostatic starts from Coulomb to Gauss, magnetostatic starts from Biot-Savart to Ampere. And then we have the divergence and the cross products, right? So let us revisit what did we achieve. Now, comparison of electrostatic and magnetostatics, del dot E equal to rho by epsilon. This was proved in the last class. Del cross E equal to 0, no name. Del dot B equal to 0, no name. Okay, del cross B equal to mu0 in J. Ampere's law, F equal to Q into E plus V cross B. So this is the total framework that is emerging, but this is not the end of the story. Okay. What is remaining? First thing that is remaining, when I'm considering just the way we did for the displacement calculation for the electric field, when some charge is moving, you know, then the question is coming here that is it a free charge or a bound charge? And what are the magnetic fields that are associated with the free charge and the bound charge, right? So the treatment remains same here. So you say that del cross Bj, this current, you have two types. One is because of free charge and the other is because of the bound charge. And free charge is like electron, that remains to be Jf, but the bound charge, you introduce a parameter like a polarization, you introduce a parameter called magnetization. Okay, and this magnetization is associated with the electron cloud, the movement of the electron cloud, which influences the magnetic field. You can understand that. Say, suppose if there is a bulky electron cloud, once the electron is moving, it will get influenced, that movement of the electron will get influenced by the presence of that bulky electron cloud. So JB, you define in the form of like, del cross B with the term magnetization, you define this as a del cross M, just the way we did E polarization, we did del dot B. Here you go for del cross M, where M you define as a magnetization. And then you bring into the left-hand side to define H. H is something like the dielectric displacement. And while B doesn't have the material properties embedded, H has all the material properties embedded, and your Ampere law reads much simpler, in terms of the free charges when you write del cross H equal to JF. Okay. Now, this magnetization again, the way we did for the polarization is proportional to what? What the electric field. Here, magnetization is proportional to the magnetic field, right? And that this proportionality constant we consider there, we consider that electric field susceptibility from where the dielectric constant came. This is called the magnetic field susceptibility chi M. This is like Newton's law of viscosity. This is like Hooke's law of elasticity, right? So, you bring in the magnetic susceptibility term here, and then, you do a kind of little bit of mathematical jugglery to get to like what is B is equal to mu0 into H plus M, mu0 into 1 plus chi M, and that you define as the mu as the magnetic permeability, which is mu0 for the free space plus 1 plus chi M. This is coming from where? This is coming from the different types of material. So you can see the different magnetic susceptibilities as you change different materials. That influence comes to the treatment associated with the magnetic field in this Ampere's law. Okay. Now, what is the consequence of that? How exactly you make use of this H? Now you can, with this H, you can differentiate something which is diamagnetic, which is paramagnetic, which is ferromagnetic, right? What is a diamagnetic material, by the way? Say, suppose if you have a material, right? Now, in that material, so suppose if you bring in a magnet. So, because of this magnet, what is the response? If this particular material develops, the opposite pole towards the north pole of the magnet, then this is a paramagnet. Okay, if this particular material creates the same pole in terms of the magnet, then it becomes a diamagnet, right? Ferromagnet is, say, suppose if you remove the magnetic field, it immediately forgets about the magnetic field. Those are either diamagnets or paramagnets. But ferromagnets is that even if you remove the magnet, then it will be able to retain some of the magnetism. Okay, so here some discussion is necessary. Before I really go back to the Maxwell's equations and all, here some very small discussion is necessary. First thing, why do you think that, a particular material will have a magnetic field? Any idea? Say, suppose I have taken a rod of steel. Suppose I have taken a rod of steel, right? So why this particular material is, question is that, say, suppose I have taken a rod of, say, chromium. Right? What do you expect? Does it have a magnetization? Does it have a magnetic field or not? Yes or no? Suppose it is cobalt, chromium. Choose a material, any material. It can be sodium, right? What does it, the decision-making factor that whether this bar is either a magnetic material, okay, or this is a kind of like, it's a magnet, or it's a non-magnet. What is that? Is there anything which is a non-magnet? Any answer? Anybody wants to attempt this question? Anything that is there which is a non-magnet?
Sir,
yeah.
Sir, due to the presence of unpaired electrons in chromium, it retains magnetism.
Very good. So first question I'm asking, is there a material which is non-magnet? Or every material has some sort of magnetism?
Sir, I think it depends on its configuration, what type of configuration it retains in its oxidized or reduced form.
Yes. So one very important point that you are raising here, that the magnetism of a material is embedded in its electronic configuration, right? Right. This is what you are trying to say, right? Hydrogen, helium, right? Hydrogen has, hydrogen has how many? Hydrogen has one, right? Helium has two, right? Hydrogen, helium. Say suppose lithium. Lithium has, 1s2, 1s2, and then 2s1, right? So hydrogen is supposed to be what? If hydrogen, which is 1s, 1, right? Helium, 1s2, sodium, sorry, lithium, 1s2, 2s1, lithium, beryllium, right? I write 1s2, 2s2. Now I take 4 materials, right? What do I expect for this hydrogen? Whether it is magnetic, whether it is non-magnetic. Now, if it is magnetic, then it is either diamagnetic or paramagnetic or ferromagnetic. What do I expect? What do I expect in case of hydrogen, in case of helium, in case of lithium? Looking at the electronic configuration, if I have only one pair, that means if these hydrogen molecules are here, if the hydrogen, I'm not talking about H2 gas, right? H2 gas is a different entity, right? H2 means, H and H, you have got a pair of electrons, right? Which nullify with each other. Whereas for each atoms, you will have, one electron, which is like this. What do I expect to happen for a hydrogen atom? Will it have a kind of like, magnetism or not?
So there should be some magnetic character.
There should be always a magnet, because if it is a single spin, say it is moving in one direction for everybody, right? So there will be a kind of like, say suppose this is one molecule, that is another molecule, this is one molecule, that is another molecule. But if you do not see in this sort of situation, if you really do not have a magnet that is in front of it, what will happen? Since these molecules are all randomly placed, right? The magnetism of this and magnetism of this will try to nullify most of the situations. So what will happen? Individual atoms may hold a magnetic field, but overall you will see a statistical average that is ongoing, where you will not see any magnetic field is manifesting. So non-magnetism is only a resultant entity, while magnetism is always there in every material in some way or other. Okay, this is the first wisdom that you get from the electronic configuration. Right now, say suppose you have a material where, say suppose, hydrogen atom and hydrogen molecule. So in hydrogen molecule you have got the spin pair, right? And in hydrogen atom you have only one electron, right? Now how exactly the magnetism of these two materials are going to change? Now let us do an experiment. Let us bring in one magnet. Say in this hydrogen atom, I am bringing in a bar magnet. I have a jar where I put the hydrogen atoms, and I'm bringing in a bar magnet here, which is this is toward north and this is toward south. And the same thing I'm doing for a hydrogen gas, where I have all the H2 with the pairs like this. Okay, and then I am bringing in a bar, which is this is again north and this is south. What do you expect to happen? What do you expect to happen here?
Sir, will it induce magnetism in hydrogen gas also?
How will it induce? What is the process? What do you mean by induction? So you will find this magnetic field will align. See, in general, it is in a random arrangement. So each one of them is nullified to the other. But moment you bring in magnet here, what will happen? All of them, since this is an overwhelming field, so all of them will get aligned to this magnet. So literally, you may see a kind of separation, an arrangement, which will lead to SNL. Because North Pole will attract the South Pole, right? And your all molecules are going to get arranged in that direction. Right, this randomness will go immediately when you bring in the magnet, and it will create an electromagnetism. It will induce an electromagnetism, and this type of magnetism is called the paramagnetism. So essentially, in presence of a magnetic field, you generate the opposite field here, right? Which is one of the basic properties where you will have the unpaired electrons. Whereas in this case, what will happen? Since there is no in this sort of situation, statistically there is no field, but this is infusing a field. So what will happen in this sort of situation? You will end up generating the opposite field, which is called the diamagnetic. So whenever you have got the pairwise summation of this, and then there is nullified things, those sort of situations, you are going to get a diamagnetic behavior. But in both the situations, what will happen? Moment you remove this external field, they again will go back to the randomness. Right? But there are certain materials like, suppose iron. If you take iron rod and if you just start rubbing a magnet on top of that, what will happen? Even when you remove, they will retain some of the magnetism inside. The order will remain even when you remove. Those are called the ferromagnets. Okay, so one big wisdom that you are getting here, everything is starting from the movement of these subatomic particles. All the properties that you are watching, it is van der Waals force, it can be magnetic field, it can be electric field, it can be magnetic susceptibility, it can be dielectric constant, it can be anything. They are manifesting because of the movement of the subatomic particles. Okay, and electric field is one of the basic fundamental happenings, because of the movement of the electrons. Most of the things, electron moving in its orbit, electron moving around the nucleus, and subsequently the nucleus, the rotation of the nucleus, and the particles that are present in the nucleus. Whatever is resultant remaining, that is what is leading to all these forces. That is number one, where electric field is at the heart of the game. Now, while the electrons are moving, what is happening? It is generating a magnetic field which is perpendicular to that, right? Now, that magnetism is dormant in every material. Why? Because there is a statistical averaging in absence of any field. However, when you bring in a field, they manifest. When you remove, they go away, but for some material, they get retained. And that is what is the difference between the paramagnetic material, diamagnetic material, and the diamagnetic material, paramagnetic material. So what is a diamagnet? What is a diamagnet? You will find here all the three definitions are given. Like, say, suppose magnetism that is parallel to B. If you apply a magnetic field, it is parallel to B, that is called paramagnet. Opposite of B, that is called the diamagnet. Okay, and those who retain, that is called the ferromagnet. So there is a history, right? So even if you withdraw, they will not immediately leave. They will just retain that magnetism. Right? Now, how do you get it? So you can see that bismuth, gold, silver, copper, water, hydrogen. You can see there is a susceptibility associated with. So these are all hydrogen means it's a hydrogen molecule. Carbon dioxide means carbon dioxide molecule. So these are all diamagnetic. Why? Because they have a susceptibility which is negative. These materials, if you bring in, a north pole will generate a north pole in those materials. Whereas a paramagnetic like oxygen, sodium, aluminium, tungsten, these are going to do what? These are going to create a north pole is going to create a south pole induce. Whereas for iron, it is not only going to create the opposite, but also it is going to retain the properties for a longer duration of time. And that's what you bring in with this magnetization, this chi-m, into your formalism, so that the material properties are also embedded into your calculations. Okay. Now, another disruption to all of your knowledge, say, what is Ohm's law? Can anybody tell me? What is Ohm's law? Anybody has any idea? What is Ohm's law?
Sir, V equals to IR.
V equal to IR. What is V?
Potential difference, sir.
What is I?
Current and resistance.
What is the origin of this V, I, and R? Any idea? From where you got this V? From where you got this I? From where you got this R? Any idea? So let me give you the answer. So this is what is Ohm's law. Next 2 slides, you are going to see what is Ohm's law. So what you say, is science is very, very fundamental. But then, the way it is taught to us, that creates a lot of miscommunications, misconceptions. And then, people generally, it's very simple and it's very logical. Anybody who is taught the method that we are using right now, I'm pretty much sure, everybody will understand, because this is so elementary. It's so fundamental. It's very easy to understand if there is a clarity. But with this mugging up and with this, the way people write books and all these things, and then, problem solving, this eagerness for this problem solving and all these things, that makes the entire concept in a very different. You see, next 2 slides, you will get the understanding from where this V equal to IR is coming. What is the origin? So the origin, what Ohm's thought that this J, this charge density, for most substances, the current density, that is J, is proportional to the force per unit charge. Okay. What is the current density? Current density is the accumulation of charges per unit volume. Right. Now, if the force is less, okay, if the force per unit charge is less, the density will be less. If the force per unit charge is more, the density, or the other way around. If the current density is more, the force per unit charge will be more. So you are coming up with a Newton's law of viscosity or Hooke's law of elasticity type constitutive relation between the current density and the force. And what you are saying that if this is the Coulomb's law, if the Coulomb's law is between the 2 unit charges, now say suppose if I have an entity which has got a lot of current density, what will be the force? What will be the consequences? Suppose I am sitting in front of this monitor. It has certain charges. What is the influence of that on me in terms of force? Is it attracting me? It is repelling me? What? So you simply say that the current density is proportional to the force per unit charge. And then you bring in a proportionality constant, which you call the conductivity. So J is equal to sigma into F. Okay. And the opposite of that, you call the resistivity. I mean, reciprocal of that, you call the resistivity. So sigma is conductivity and 1 by sigma is resistivity. By the way, conductivity and resistivity are fundamental material properties. In V equal to IR, what is R? In V equal to IR, what is R? It's called resistance, right? That resistance is not resistivity. That is not a fundamental property. Resistance is not a fundamental property. Resistivity is a fundamental. Resistivity, viscosity, conductivity, these are all material properties. Susceptibility, there'll be a Y at the end. Permeability, right? These are all fundamental properties, but resistance is not a fundamental property. Okay, it varies with the geometry. For a cylinder, if you have a copper, if you take a cylindrical copper wire, if you take a rectangular copper wire, the resistance will be different. Resistance is a property that depends on the geometry. But resistivity and conductivity is a material property for copper, for a cylindrical copper surface, for a rectangular copper surface, for both the cases. Since it is copper, resistivity is going to remain same. Okay, so the first origin of this Ohm's law is the electromotive force. Right? What is the force that is in origin? So now you say that, so J is equal to what? You have said J is equal to force per unit charge, and force, you know, Q into E into V cross B, right? So you put Q. Right? So F, capital F by Q is small f, and that is equal to E plus V cross B. Now you consider this to be electrostatic and put V cross B equal to 0. So J, the current density, is equal to sigma into E. So that current density is proportional to the electric field, and the constant is coming out to be what? That is sigma, which is what? Which is the conductivity of the material. This is the fundamental, the most fundamental, you know, formulation of the Ohm's law. Okay. Now 1 by sigma is rho. The resistivity, you can see this is for silver, copper, you know, the different types of resistivities have been given. Resistivity high means it's an insulator. Resistivity low means it's a conductor, right? So this type of demarcations we can do. This is a fundamental form of the Ohm's law. Now, once we have obtained this, then we go for, by the way, I just leave an assignment here, okay? J equal to sigma E, okay? Try and derive V equal to IR from here. Okay, it's available on the internet. I generally don't give it, right? So just derive it. J equal to how J equal to sigma E gets converted into V equal to IR, and why resistance R is not a fundamental property of a material. Rather, it's a more of a kind of, it's a cooked up property. Although it is very, very much useful in terms of calculations and all, right? But the original Ohm's law is J is equal to the current density is proportional to what? Proportional to the electric field. Right? Now, once we are done with that, I am remaining with only one correction, and that was done by the genius of Faraday. So what he did, you know, he did 3 very simple experiments. What is the first experiment? Say you have a magnet and you took a solenoid. Solenoid means it's a copper wire, and then there is a resistance here, and he to put up an ammeter. Now, if in this sort of situation, say suppose you have the magnet and you have the solenoid, right? Now, if you pull the solenoid in this direction, if you just take the solenoid out, keeping this B stationary, you may observe a current here. Nothing has changed. You just moved it. He saw a current. Then he kept this wire stationary and he moved this magnet. Then he saw there is a current. Third experiment, what he did, he kept both of them stationary. But this, you know, this magnetic field, you know, he kept changing with an electromagnet. So he saw again, just by fluctuating this magnetic field, you know, he got the current. So these 3 experiments actually told that, you know, if there is a variation in the electric field with respect to time, it is going to change the magnetic field. If there is a variation in the magnetic field with respect to time, it is going to change the electric field. And that led to the correction that, you know, this del cross E has a component, right? It came from, like, you know, E is equal to cyclic integral of E dl, which is d phi by dt, and E dot dl is equal to del d by del t. 1 minute. Yeah, so you can see that a changing magnetic field that induces an electric field. Okay. Now, what is the change? So you consider the phi, which is changing with respect to time, and that leads to the line integral of EDL, which you convert to E is related to the change of B with the equation E dot AL equal to integral of del B by del T, which led to that del cross E in absence of any magnetic field fluctuation is 0, which is the fundamental property of the electric field. But if alongside the electric field, if there is a fluctuation in the magnetic field is going on, so you have a correction for del cross E like this, which is del cross E equal to minus del B by del T. This is one important correction to the Maxwell's equation. The other consequence is that this is the correction to the del cross E. What is the other correction to? That is del cross B. So you may see that subsequently the variation in electric field also is going to influence the. So earlier we proved that del cross B equal to mu 0 J. But then fluctuation in electric field also is going to change the magnetic field. So that change you introduced as mu 0 epsilon 0 del E by del T, which is called the Maxwell's correction to the Ampere's law. Okay. So del dot E equal to 0, rho by epsilon, that is Gauss's law. Del cross B equal to 0, there is no name. Faraday's law is del cross E equal to minus del B by del T, and del cross B equal to mu 0 J plus mu 0 epsilon 0 del E by del T, that is Ampere's law with Maxwell's correction. So this is your set of Maxwell's equation that is proven. That is the most fundamental set of equations for electromagnetic field. With you have F equal to Q into E cross B, that is the force, and del dot J equal to del rho by del T, which is the continuity equation. So if you understand this framework, you are able to really tackle any electric field, magnetic field related problems. We are going to tackle it today, so that you can see that how exactly these things are done. Right now, these equations can also be written in terms of displacement. Right. So this is the same set of equation we have written in terms of this is electric field displacement and this is the magnetic field displacement. This is the polarization, this is the magnetization, this is the electric field displacement, this is the magnetic field displacement, right? And this is the displacement current. So including the material properties, these are the ones where I'm writing independent of the material properties, but where I bring in all the material related aspects. These are the set of equations which I have explained one by one beforehand. Right. Now, once you do that, now let us revisit how exactly force and stress are to be correlated. So force is equal to what? E plus B cross B Lorentz force rho d tau. This is my Q. Charge per unit volume into differential volume over the volume integral, right? Now, so F is F is force per unit volume is because in Navier-Stokes equations I am going to in all the momentum equations I am going to take force per unit volume and then I am going to take a volume integral there. What is that? That is rho E into J cross B. What is rho? From Gauss's law we know that del dot E is equal to rho by epsilon, right? So rho is equal to what? Divergence of E into epsilon 0. So I replace this rho here with this. So you can see here this term comes from there. Epsilon 0 divergence of E into E. I am coming from here. Okay. Now J cross B, J is what? I'm taking J from here. This del cross B minus this divided by this, right? If I do that from the Ampere's law, I will get this. So this part is coming from the Ampere's law with Maxwell's correction into cross B, J cross B, right? Now I use an identity. Del T of E cross B is this. And that I replace here. And Faraday's law tells me del B by del T is equal to minus del cross E. So if I make use of these two and replace back here, I get this particular term. This is the electric field part, and this is the magnetic field part. Okay. Now, I use a vector identity, which is E cross del cross E is equal to this. This is a vector identity. I make use of it. And if I replace back, in this equation, in 8.17, I end up getting force equal to this. Okay, so this is the force per unit volume. This is the force per unit. This is the force per unit volume. Now, if that force per unit volume, this force per unit volume is written as a divergence of T, where T is the Maxwell stress tensor. So this is the force per unit volume. If this is to be written in the form of divergence of T, T comes out to be something like this, where Tij is epsilon 0 Eij 1 by 2 delta Ij E square and 1 by mu 0 Bibj delta Ij B square. So this is your Maxwell stress tensor, where this part takes care of the this part takes care of the magnetic field and this part takes care of the electric field. So one assignment, starting from here, please derive the entire part. It is there in Griffiths. So if you just follow Griffiths, so you will find in chapter 8, entire derivation is given. So you need not do anything. You just follow this line by line, in this chapter. Just look at the way it has been done, right? This entire thing, what has been told in this particular class, in this particular lecture, is from Griffiths. Okay. So we started in the last class from chapter 1. Right now we are at chapter 8. Okay. I'm just galloping because you just need that sort of information. So you just do all these things by yourself to get more hold of. If you don't do, if I do it, you will not have the control over all the things. Right. So that's the reason I have just shown you. This is something like the stress tensor tau ij. Okay. The sigma ij. Right. Exactly similar like that. So essentially, this is the force per unit volume expression for, and this is the stress associated with that. This is the stress tensor. So the different directions how the forces, the force per unit area will manifest. That you get, because of the movement of the electrons, because of the movements of the charges, electrons, holes, and so on and so forth. Now, bringing the entire thing, whatever we have studied, into this system. Okay, if I don't prove it, then you will not really understand that how this is effective. So what was our problem? Our problem was there was an electrode, there was another electrode, and there's a film in the middle, and this film, liquid film, is deforming. Right. So what is the equation that I'm using? I'm using del dot E equal to 0 because I consider this to be insulator. Right. I don't consider there is any charge other than the charge at the interface. The bulb, there is no charge. Even if there is a charge, that has become electroneutral because of plus and minus. So del dot E is equal to 0, del cross E equal to 0. So E is equal to minus this, del cross E equal to 0 is leading to this. So this is my Laplace equation. Right. So let me just do a very quick calculation how simple it is once you understand the whole thing in a very clear manner. So you can really understand that. So suppose I am doing a calculation for an electric field. This is a electrode. Say suppose this is the air. Say suppose this is a liquid. This is a dielectric liquid. And suppose this is the electrode. This is another electrode. Okay. Say I call this as 1. I call this as 2. So, and then these two electrodes are integrated to what? These two integrateds are electrodes. So this is minus, this is plus. So this is about 10 volt. So suppose this is about 0 volt. Now I need to know what is the electric field here. So what should I do? I should first solve del square psi 1 equal to 0 and del square psi 2 equal to 0. Essentially, what am I solving? I'm solving del dot E1, okay, equal to 0, and then del cross E1, which is equal to 0, which is giving me E1 equal to minus gradient of psi 1. And this I am replacing here to get del square psi 1 equal to 0. Rho I will come later. For the time being, I will show you where this rho is to be taken. For the time being, I consider entire things to be charge neutral and there is only a field associated with these free charges. Bound charges, they are getting accumulated here, that I will manifest in a different way. Correct? Can anybody narrate me what is my del square psi 1 equal to 0? What should I write in a differential form? What should I write? Del square psi 1 equal to 0. Quickly, prompt karo. Del square psi 1 by del x square plus del square psi 1 by del y square equal to 0, right? Say this is, suppose this is y, suppose this is x. Okay, and what will be my del psi 2? Del square psi 2 by del x square plus del square psi 2 by del y square equal to 0. These are my two equations, right? इसको ये लिख सकते हैं, इसको ये लिख सकते हैं. Am I correct? Now what I say that, since the field is applied in the y direction, the variation in the field is very, very less. So I just ignore it. If you do a long wave approximation, it will go away. If you do an order of magnitude analysis. So I convert this to an equation of d square psi 1 by dy square equal to 0 and d square psi 2 by dy square equal to 0. This gives me a solution of what? Psi 1 equal to C1y plus C2. Psi 2 is equal to C2y, C3y plus C4, right? Now I have to get C1, C2, C3, C4. So what is the psi 1 at y equal to 0? Can anybody prompt me? At y equal to 0, what is psi 1? Psi 1 is equal to what? At y equal to 0?
C2.
At y equal to 0, psi 1 equal to what? Boundary condition. Of course, it is C2, but boundary condition is what? I have applied a voltage, no?
It's 10.
It's 0, right? At y equal to 0, it is 0. And at y equal to, this is, suppose this is my thickness h, and this distance is, say, suppose d. This entire distance is d, right? So that then at y equal to d, what is my psi 2? Psi 2 is equal to what?
10.
10. I say that is to be 10 को मैं
10.
बोलता हूँ कि एक voltage B. Okay, psi 2 equal to V. What will happen at y equal to h? What will happen to the psi 1 and psi 2? I can consider psi 1 equal to psi 2. And then I will have another one, epsilon 1 del psi 1 by del y1 is equal to epsilon 2 del psi 2 by del 2. So essentially, del psi 2 by del y. Del psi 2 by del y and del psi 1 by del y. Essentially, for C1, C2, C3, C4, you need 4 boundary conditions, right? So this is the one boundary condition. This is the, see, here you have one boundary condition, here you have one boundary condition, here you will have 2 boundary condition. If you enforce these 4 boundary conditions, you will be able to get what is psi 1 and what is psi 2. Because if you enforce these 4 boundary conditions, you are going to get C1, C2, C3, C4. So if you have expression for psi 1 and psi 2, you have the expression, you know what is E1 and E2. Okay, once you know E1 and E2, you know what is T1 Ij and T2 Ij. And then you can integrate back that in your equation, which is, say, suppose, on a rho dV by dt equal to minus gradient of P plus divergence of sigma plus tau plus M, a tau plus T here I write, okay, which is coming from the Maxwell stresses plus rho G. Right? So that's the way it has to be done. So I've just done a kind of very elementary calculation for you, so that you become more comfortable. Now I go back to the calculations here. You will understand this very easily. So what is my concern here? What are the governing equations for this particular system? It's divergence of E equal to 0, del cross E equal to 0, E equal to psi. That gives me del square psi equal to 0. This is the continuity equation. Now in the Navier-Stokes equation, I'm starting with the simplified form because order of magnitude analysis I have already done. So I am considering that to be what? This sigma I am considering Newtonian fluid. Okay, and then M I am reducing. Why? Because if the film is charge neutral, in the bulk, the divergence of M will be 0. Because I have considered the divergence of E to be 0. If I write the Maxwell stress tensor like this, which is nothing but what we have written here, this is nothing but this. Okay, so it is to be 0. So divergence of M to be 0. So this is the framework that we are sitting with, right? And how will be the boundary conditions? Of course, in this case, U equal to this. These are the flow boundary conditions, and these are the boundary conditions we have already gone through. This is the thin film equation for this. This is the normal stress balance, and this is the tangential stress balance. But you have to understand how do we take care of now the electric field. This we have already done in the last class. Now here, phi we will consider to be the electric field. Okay, this phi will come for the electric field. How to do that? That's where we are debating. So how are we doing? Del square psi p by del z square equal to 0. Just now I have done that. Del square psi a equal to 0. The psi p equal to psi b at z equal to 0. And psi a equal to 0 at z equal to d. Right? Psi a equal to psi p and epsilon. I have just taken those boundary conditions. If you enforce into this, what will happen? You will get for polymer this equation, for air this equation, right? And then what is the phi electric field will come? Phi electric field will come. If you this this will come from the normal stress balance, and I'm going to show you how this particular thing comes, right? So you can see that if you know psi a, if you know psi p, you know phi el, and that phi el goes here as phi. This phi is for the electric field. This one that you integrate, and the electric field comes from where? Electric field comes from the gradient of psi. From there, this is the electric field that is prevalent into the film. Okay, so now you can see the normal stress balance. This is your EL coming out to be phi EL coming out to be, which is coming out to be like this. I have just given all the steps for you so that you verify. So this is the if you expand this Maxwell stress, I have just written down everything so that you need not redo. If this is the Maxwell stress, this if I expand into a tensorial form, it comes out to be like this. Now, since we are writing E is a gradient of psi, if I expand, in terms of gradient of psi, it comes out to be like this. Okay. Now what you do, just like you have done for what? So T is this is your pressure, thermodynamic pressure. This is your viscous Newtonian viscous force, and this is your Maxwell stresses, right? And then when you take the normal balance, what do you do? N dot T dot N minus N dot T dot T. This is what is happening at this interface, correct? This is what is happening at this interface. Here you are going for this normal stress balance and tangential stress balance, right? Now, how do you do that? You see that, you just bring in the entire thing here and that N dot N. Okay, and if you do all the steps very, very carefully, you will end up getting, this equation. And here, if you just ignore this del psi by del x whole square, you will end up getting which equation? You will end up getting this equation. Okay, which you consider to be this phi EL, which goes where? Which goes here, which goes here, in order to come up with your thin film equation that is associated with the electric field. I request all of you, this may be one of the questions in our end-sem examination. I may request you to derive the entire thing step by step to convince me that you have understood. Okay, so here you can see this is the thermodynamic pressure, this is the viscosity part, okay, and this is the electric field part, which is coming from where? You are taking this to be thermodynamic pressure. This is the Newtonian stress tensor and a hydrodynamic deviatoric stress tensor, and this is the electric field coming from the Maxwell stresses, in order to get all three components equal to gamma hx. And then you can see that this is converted into phi. So this phi can be used for the van der Waals forces. This phi can be used for the magnetic field. This phi can be used for the electric field. The formulation goes to any direction you like. Right? Any question up to this point? Any question up to this point? Any question up to this point? No questions.
Sir, can you explain the last page derivation again?
Yeah. So let me go back to this particular framework. What are we trying? So what we suggested that, let me go back to the experiment first. Because this experiment was discussed previously. Now, what's going on here? Now let us see what we understood. In that, let us interpret the things. So what's going on here? So I had a film, liquid film, and I have applied electric field just by bonding them together. And I saw the films have started deforming like this, right? And they form the column. What's going on here? Okay. So I have ensured that this is a parallel plate capacitor configuration. There is a liquid film. This is liquid. So this is air gap. And then there is another electrode on top of that. So, and then there is no current here. So essentially anything that is happening, that is because of the bound charges. I have ensured that, how the free charge treatment will be done. I'm immediately going to discuss another problem with you. Okay, so that you also come to know how the free charges are to be treated when a system conducive to that. But this system is a bound charge because there is no current. It is only say suppose you have accumulated all minuses here, all pluses here, and because of that there is a polarization of the molecule. So this is minus, this is plus, this is minus, this is plus. So there is a plus polarization here. And then there is a minus polarization here. And then these molecules are also aligning across the electric field. They are not flowing. They are basically aligning their electron cloud as per the field that has been assigned. Now, since that has happened, there is a stress that is generated because these bound charges are of same type. This side, both sides. And that is the reason you generate this Maxwell stress, this Tij, that is across the interface because of the electric field. So because of the electric field, there is an additional stress. So now what is my continuity equation? Del dot U equal to 0. I keep it like that. What is my force balance equation? Rho dV by dt is equal to minus gradient of P plus divergence of, say, tau. I put this Maxwell stress here, because that is going to manifest here, right? And then I ignore this rho g. I ignored this rho g. I ignored this because there is no flow here. This is a stationary fluid. I'm just, it's a very low Reynolds number situation. So what I say that this is implies this is 0 minus gradient of P plus divergence of tau plus M. And I consider that there is no free charge, rho F equal to 0. Right. And I also considered that influence of the bound charges are 0 even in the bulk. So that, I can say that del dot E, which is in general equal to rho by epsilon 0, I say that in this case, I simplify this to del dot E equal to 0. Moment I enforce that, when del dot E equal to 0, del dot M is also 0. So my governing equation becomes, 0 minus gradient of P plus divergence of tau. It remains to be the same. That is there in case of, so what it is saying that although there is a charge separation, but there is no net charge in the bulk. There is no net charge in the bulk because each of these charges, they are cancelling out. There is a statistical average. Only the charges are manifesting. The charges are only manifesting near the interface, something like this. Right? This is what this formalism says. Then what I do, I go for my standard normal and tangential balance. What are the balances what are the boundary conditions that I need to do? At Z equal to 0, say suppose U equal to Z equal to 0. No slip and impermeability, right? U equal to W equal to 0, no slip and impermeability, right? At Z equal to H, I have thin film equation, del H by del T plus U del H by del X equal to W, right? What are the other two equations that I have? I have N dot tau plus M. Now I have added this N. This is for what? This tau A and MA minus N dot tau liquid plus M liquid dot N. This is equal to gamma kappa. This is my Young Laplace equation in presence of the electric field. So I have added this Maxwell component. And then what I have the tangential component N dot tau A plus MA dot T is equal to N dot tau A tau L plus ML dot T. Okay. So this is my overall definition of the problem. And then this at the interface, this additional stresses, which is essentially creating the phenomenon. So let us revisit the entire problem the way we have defined. So how are we defining? By the way, you know, these boundary conditions that I had written now, I had written two quick boundary conditions saying that, see, at the interface for when I'm solving the electric field, at the interface psi1 is equal to psi2. And the other boundary condition is epsilon1 del psi1 by del x is equal to epsilon2 del psi2 by del x, right? So these two boundary conditions are coming from where? From these two. So for electric field also, you can take a normal and tangential balance at the deformable interface, which you have to use in order to solve this equation. And these two comes from the simplification of this. Okay, now revisit at this equation. Now revisit at this equation. So this is my continuity equation. This is my Navier-Stokes equation. It doesn't change much because, you know, the bulk is charge neutral. And this is my normal stress balance. But you know, here I did not consider the electric field. Here you see I have added this phi as an electric field. Now, how do I calculate this phi as an electric field? What is the influence of that phi? So I start solving the equations at both the layers. Okay. Now, this is I have defined already. Psi equal to psi b at z equal to 0. Maybe this is the other way around. People have applied. You can apply the way you like. The equations will not change. Right? It doesn't matter which direction the anode and cathode is. Correct? So these are the ways you have applied the voltage, and these two are coming from where? These two are coming from these two equations. Okay, these two equations are coming from. So for electric field also, I get the continuity of the electric field at the deformable interface with respect to what? So this is the normal and this is the tangential. Right? So this electric field vector, I do a normal and tangential balance to get these equations so that I get psi p and psi p, expression of psi p and psi a. Moment I get the expression of psi p and psi a, I know the electric field and I also know the Maxwell stresses. Then I say, now this comes from the normal balance. From the normal balance across this interface, whatever we have written, it comes from there. This is the normal balance equation. And in that normal balance equation, phi I can be the van der Waals force and other forces or the gravitational forces. I keep the phi EL component and I debate how this is coming in the normal stress balance. How this is coming? So I say that this is my Maxwell stress. So if I really need to write the T, so I have seen this is coming from the thermodynamic pressure, which is the 1/3 of sigma 11, sigma 22, sigma 33. This is my Newtonian for a Newtonian constitutive relation. This is the Newtonian for a Newtonian fluid. This is the relationship between the stress and the strain rate. Then what I do, I add the Maxwell stresses at my. So this is my minus gradient of P. Okay, no, this is only P minus P plus this is sigma. Sorry, so this is tau plus this is M. So I'm writing these three things together because I have applied the electric field. Now on that, what I do the normals. This is my generalized Young Laplace equation. Right? So earlier it was only in terms of P, then we graduated with the tau, the deviatoric stress, then I'm adding the Maxwell stress here. Right? Now, once you do that, you bring in the entire thing in between this. So this is your what? This part is what? This part is, P delta Ij, mu del I, del Uy by del Xj, epsilon 0 this. So this you are bringing in from here, right? Dot n equal to gamma kappa, right? Now, if you do that, if you take this n dot n, if you embed here, you end up getting this equation, where this is the pressure component, this is your viscous component, this is, I think, yeah, I have added the viscoelastic component also, and this is your electric field component. This will be coming from what? N into M into N. If you do that, you will get this. Okay, so you can see the phi EL that is coming out to be something like this. If you ignore the X component, considering that the field is applied in this direction, if you ignore the X component, it is going to come like this, which is the one which you can solve and you can imply here. Could I answer your question? Is it clear? Where is the doubt? Hello? Yeah, could I answer your question?
Yes, sir.
Is
Yes.
there any doubt? Where is the doubt? A lot of doubts are there, right? Because you have seen this for the first time. So what you do, all of you, derive this line by line and submit as an assignment. Okay. And if you face any problem, come to me and discuss. Okay, there will be a lot of confusions here because I have jumped a lot of steps. Right. So overall, you will find that any electromagnetic thing that we have to start, right? We have to first start here. Then we have to consider this to material. And then we have to come here. Now, these are the three things we have to bring into the framework in order to do that. I'm going to show you a few more examples quickly, because it is very, very important. These are all happening at the micro nanoscale. That is why this is very different. This type of dynamics is very different from what generally you see in the macroscopic domain, right? I take an example that, say, suppose I use this Lorentz force to make a fluid flow. These are called the magnetohydrodynamic pumps. So you have a micro channel. Okay, you have embedded some electrodes like this through which you have applied an electric field. This is the vertical electric field that you applied. These two electrodes, you have applied a vertical electric field, and you have put two solenoids just beside this, which is generating a magnetic field like this. So there has to be a current first, I, between these two electrodes. That means the liquid has to be conducting, and there has to be a magnetic field in this direction, because if you put a magnetic to a conducting liquid, so current is flowing, and then if you put a magnet on that direction, so you are going to generate I cross B, a force in the direction of the flow. So there will be a thrust. So if you have an electric field in this direction, if you have a magnetic field in this direction, you can put it. Say in micro scale, in nano scale, if you really want an impeller, that impeller has to be very small. You have to fabricate, you have to rotate, very difficult. More importantly, the frictional forces are so high, you cannot really rotate an impeller and then pump it. So these electromagnetic forces are used, piezoelectric forces are used, in order to pump them. So this is one of the micro pumps where you use the Lorentz force in order to force the fluid. Now, how do you get into the equation? So again, you have del dot U equal to 0. This is your velocity continuity equation. Then del dot J equal to 0. This is your current continuity equation. Okay. Now rho du by dt, gradient of P mu du square. This is your, this is your Navier-Stokes equation. But instead of rho G, you enforce J cross B. What is J cross B? J cross B is this I cross B, right? J will be the volumetric one. So you apply J cross B, right? Where J is equal to sigma. Just now we are studying minus gradient of phi U cross B, where B is the electric field and sigma is the is the conductivity. Right? If I expand these equations, you will find this is the two-dimensional continuity equation. This is the Navier-Stokes equation. This is the local acceleration, convective acceleration, pressure, viscous forces. This is the Lorentz force that is applied. This is the Lorentz force in the y momentum. And this is what? This is nothing but divergence of J equal to 0. So if you solve this sort of equation, you are able to model the magneto-hydrodynamic flow inside a channel, which is very similar to the flow you are having with a pressure drop or a kind of, a gradient due to the gravity. The same framework can be used. That's the reason why we are working hard for last 2.5 months in order to make this sort of flow happen. Any doubt here? Any doubt here? So you can see that B has been written as BEZ because magnetic field will be in only one direction, right? So that you just notice. Again, I will suggest all of you to submit this as an assignment. Just derive this thing, this entire chronology of events. That there is a geometry, there is a geometry, and then you are making the flow like this. So you have this electric field is in this direction, and magnetic field is the perpendicular to the plane of this computer. And then you are making a flow in this direction, right? You need not go up to parabolic profile, this, that, nothing. But just write down the equation from the top, the vectorial equation. You end up deriving this equation and submit this. Okay. Now, if you want to really see the electroosmotic flow is a little bit different from what was happening there, right? So what is an electroosmotic flow? Again, electroosmotic flows are used to pump in microscale. In microscale, you cannot pump by this pneumatic means. There are syringe pumps and all, but that is for a macroscopic, I mean, in milliscale, about 100 micron, about 50 micron, about 10 micron, it is possible. Lower is the dimension, difficult is to push it through pump because of the increase in the viscosity. So how do you do that? How do you make sure? Now, say suppose if you have two electrodes, this is another interesting concept. If you have two electrodes and one of the electrode is having say you make sure that the electric field is such that both the electrodes are negatively charged. And you put a very weak electrolyte in the middle. Okay, so what is the recipe for the electroosmotic flow? You have a channel, in that you have put an electrolyte. Electrolyte means it is having plus and minus ions embedded. This is an ionic flow. Plus and minus ions are embedded inside the channel. Okay, and you bound it by the electrodes which are say of same charge. Say suppose you are bounding this by minus electrodes. Right? So in this sort of situation, what will happen? If you apply an electric field here, say suppose if you apply a plus, and if you apply a minus here, you will see that there is a movement of this fluid. And why this movement of the fluid happens? There is a reason behind that. The reason behind that is the formation of the electrical double layer. How does that happen? So suppose I have a channel. Okay, and this is negatively charged. I have made the charge. I mean, this is a cylindrical channel, and I have made it negative. And I have put an electrolyte here. So if you put the electrolyte here, it will form a immobile strand layer. Some of these ions will get attached to this minus. This is called the strand layer. Named after the scientist who invented this. Okay, so in both sides you will have a strand layer. Right? But this strand layer is an immobile layer. This is an immobile layer, but there will be some pluses which are roaming around nearby, but they are not immobile. That layer is called the diffuse layer. In both sides, the counter ions, will make a situation, right? Some of them are fixed and some of them are floating around. Now these two together is called the EDL, or the electrical double layer. Okay. Then as you go gradually towards this, the core of the fluid will be electroneutral. There will be no net charges here. Okay, but then just near, and this thickness is, suppose this channel is your about like, say 10 micron, this will be maximum, this thickness will be maximum about 100 nanometer. Essentially, this is about 10 to 50 nanometer. So if you have a channel like this, you will, and this is charged, this is negatively charged, you will see that there is a very thin layer which will form the electrical double layer. This is a very thin layer which is from the electrical double layer. And this is a kind of like, this is a charge neutral core. Okay, and in that sort of situation, if you just put a electric field like this is plus and say suppose this is minus, what will happen? This plus charges will start moving. This electrical double layer will start moving towards the negative. So essentially, you will observe a flow where like these charges are moving towards this negative charge, and you will end up getting a flow profile something like this. Right, where this boundary layer flow, this boundary layer movement, the movement of these pluses towards this minus will drag the core fluid towards the electrode where it is getting attracted. And this type of flow is called the electroosmotic flow. Okay, let us just check. Now you see that we are getting into a hardcore game of, up to this point, see the previous example, previous example was purely, I have excluded rho F, rho B, everything. Here, I have considered conductivity. Okay, I have considered conductivity. I have considered a current. That means free charges are moving. In this one, I have the free charges as well as the bound charges. Now you see how are we doing. So for liquid, continuity is del dot V equal to 0. For the fluid, for the momentum, rho dV by dt, gradient of P B del square V remains same. Now for electroosmotic flow, I introduce the term called rho. I introduce the term called rho into E. E is the electric field and rho is the charge density. Now E I define as minus gradient of phi plus psi. What is this phi? Phi is the electric field. Phi is the electric field in the vertical direction because of the electrolyte and the charge separation. That is my phi. And what is psi? Psi is the so phi is associated with a very thin layer that is near the boundary. That I am going to solve using the Poisson's equation because I have a free charge here. Whereas since the bulk is electroneutral, I am using again the Poisson's equation. So psi is essentially the flow of the neutral core. And I define this E equal to psi plus phi. Right? And what is the solution of phi? Del square phi, E epsilon 0 del square phi equal to rho. This is the Poisson equation. This gives me phi and this gives me psi. Now, if I replace this in this equation, what do I get? You see, I get rho into this del P by del X. This is the viscous term. How do I get this? I have rho into epsilon, right? So what is rho? Rho I can write epsilon 0 del square phi. And what is E? E I write gradient of phi plus psi. So this is a consequence of that. This is a consequence of that, right? So I have taken care the formation of the electrical double layer, and I have also taken care of the electric field flow that is happening because of that. Now, what are the boundary conditions? So phi equal to phi zeta says at the walls. Okay, and psi equal to constant, psi equal to 0, just the way we have done. This is a kind of voltage applied V. This is equal to 0 because of that. So if I solve the second order equations with this boundary condition, if I get psi and phi, if I embed psi and phi here, if I solve this total equation, I will be able to get the velocity profile like this. So this is the way the electroosmotic flows are modeled inside a microfluidic channel, and this is called the electroosmotic pump. Again, please derive these things on your own. I have given the entire summary of the events. It's very simple and very interesting that how, the framework that we develop. Now, this is for only Newtonian I'm showing. It can be for elastic film, elastic materials, you can do it. You can for viscoelastic materials, you can do it. It is your game that, how do you change these things as per your wish. You can bring in electromagnetic field here. You can bring in anything. This is the framework which is going to be applicable, anything that you are going to do. And this is where perhaps, people started thinking that there is a universality associated with all the processes. And how exactly after that the science developed that, can you come up with a kind of universal theory, which can be like, in asymptotic limit, all the phenomena can be, is there an universal law? Right? So yes, so I stop up to this point. Any question? Any question? First thing, have you understood everything up to this point? Any doubt is there?
Hello, sir.
Yeah.
Sir, in that normal balance, why there are two n dot the stress tensor dot n?
So, you have the components, no? So when you discuss about that, say you have this deforming surface, right? So at a point you are trying to enforce the force balance, correct? And then you are saying that you are going to force balance means you are going to balance the normal and you are going to balance the tangential. That's the way the force balance will take place. Now, when you are talking about the normal for a layer 1, so you start with the stress tensor sigma ij, right? Now, say suppose if I look at in 2 dimension, if I write, these are my sigma ij, right? This is xx, this is xy, this is yx, and this is yx, and this is yy, right? Now, when I take first normal n dot sigma ij, when I take, I get these two. And then when I take the second one, I get this one. So essentially, by taking 2 normals, I get sigma yy, the stress component that is in the normal direction.
Okay, sir. Thank you.
Correct. And then when I take t, I get, since these are symmetric, I get any one of them, doesn't matter. So that is equal to n dot sigma ij dot t. Any other question? Any other question? No, if not, thank you. So we meet. Acha, when is the what is the date that we fixed for the presentations? Next Wednesday, right? Am I correct? Hello. So
No,
next
sir, I
week.
think 30.
Huh?
I think 30.
30th or
March,
23rd? 30th or 23rd March?
30th, I think.
So
30th.
30th.
Okay, okay. So 30th, 23rd, then we meet at 6, to discuss further all these aspects. Okay. Yeah. Thank you. So for 30th, you people should make preparations. Okay. I'll discuss on 23rd class. Thank you. Yeah.